Okay, so hello everybody. It's a great pleasure today to welcome Andrea Sciandra. I'm not totally sure I am well pronouncing your name, but sorry about this.
Yes.
From Torino, I think.
Yeah.
And he's going to talk about Drinfeld post-Hopf algebras and Drinfeld relative Rota Baxter operators.
Okay.
With you.
Thank you. First, I thank the organizers for this opportunity. I would like to start by recalling some definitions coming from Lie algebras that motivate this work. So, in 2007, Ballet introduced the notion of post-Lie algebra, which is, in fact, a Lie algebra equipped with a linear map from G tensor G to G, such that these two conditions are satisfied. And let us analyze this a bit. So first of all, you can define this as a new bracket on G. In fact, 1 and 2 tells you that on G, this make G a Lie bialgebra, the so-called subjacent Lie algebra. And then 1 and 2 tells you that, in fact, you have an action of the subjacent Lie algebra on the starting Lie algebra. In fact, as you can see, fixing the first entry, you have a derivation, and then this other one tells exactly that you have an action of the subjacent Lie algebra on the starting Lie algebra. If you assume that the bracket is trivial, then one recovers the previously known notion of pre-Lie algebra. So it is just a vector space equipped with a linear map that satisfies this condition here, just putting here this to 0. And that's all. On the other hand, we have the definition of Rota-Baxter operator on a Lie algebra. I also put here the more recent definition of Rota-Baxter operator on a group, because we will use it in a specific point, but we are more interested in the one of regarding Lie algebras. And I will say relative Rota-Baxter operator always meaning of weight 1. So first, let us recall the definition. And given an action of a Lie algebra H on a Lie algebra G, then a linear map T from G to H is called a relative Rota-Baxter operator on H with respect to G if the braiding of Tu and Tv, so the image of two elements through T, is in fact given by the image of T of what? Of the bracket of U and V, plus the action of Tu over V minus the action of Tv over U. Analogously, one can define, given an action of a group H on a group G, an F R from G to H is a relative Rota-Baxter operator on H with respect to G if the product of these two guys, Rg and Rk, where G and K are elements of G, is given by the image through R of the product of G with the action of Rg on K. Now we have this result when we start with a relative Rota-Baxter operator on a Lie algebra H with respect to G, then the domain becomes a post-Lie algebra, just using the action, in fact, that we have of H on G. In fact, U acting on V is just given by the action of Tu over V. Vice versa, if we start with the post-Lie algebra, then just choosing the identity morphism gives us a Rota-Baxter operator on the subjacent Lie algebra, where in fact the bracket is just given by this, as I told before. So when we start with a relative Rota-Baxter operator, we are able to obtain a post-Lie algebra on the domain of it, while if we start with the post-Lie algebra, this gives us automatically a Rota-Baxter, the identity gives us automatically a Rota-Baxter operator on the subjacent Lie algebra. So on a recent paper, Li, Sheng, and Tang introduced the correspondent notion in the Hopf algebra setting, post-Hopf algebra, and relative Rota-Baxter operator on a commutative Hopf algebra, providing an adjunction between these categories under the assumption, in fact, that all the structure involved are cocommutative, and so generalizing, in fact, these values a lot. What we want to do now is to generalize this result by removing the cocommutativity assumption. So obtain an adjunction between analog categories, let's say, when we remove the cocommutativity of the structure involved. So first, I would like just to recall what an Hopf algebra is and what a braided Hopf algebra is. In fact, we will need also the notion of braided of a Hopf algebra in a different category, different from vector spaces, I mean. So first of all, a bialgebra is just the datum of an algebra, which is also a co-algebra, such that we have a compatibility between these two structures, meaning that the coproduct, so first of all, the co-algebra structure, we have a coproduct which goes in the opposite direction of the product, so from B into B tensor B, and we have a co-unit epsilon, which goes from B into the base field, and they satisfied co-associativity and co-unitarity dually to the axiom of an algebra. And we also require that delta and epsilon are morphism of algebras, or valently that M and U are morphism of co-algebras, meaning in exactly this condition here. You can see delta here is epsilon is multiplicative and epsilon is unitary. This one is delta is unitary, while this one is delta is multiplicative, and with the A1 and A2, we just mean the delta applied on A and just omitting the sum using the Swidler notation. A Hopf algebra is, in fact, a bialgebra together with an antipode, which is a convolution inverse of the identity in the endomorphism, in the K endomorphism of B. So it is just a linear map from B to B, such that this condition is satisfied. Again, B1, B2 just mean the coproduct applied on B. Hopf algebra is cocommutative if the coproduct is, in fact, the coproduct followed by the twist, the flip map, which on elements means this. So this is exactly the dual condition of being multiplicative. And the classical example is, in fact, the group algebra, which is a cocommutative Hopf algebra, where the coalgebra structure is the group-like coalgebra structure. So delta on an element G is G tensor G. The co-unit on G is the unit of the base field, and the antipode of G is given by the inverse of G. Now, the category of Hopf algebras coincide with the category of Hopf monoid in the category of vector spaces, but one can define also operates for an arbitrary braided monoidal category, which is so a monoidal category with a tensor product and the unit object, and a braiding that satisfies the so-called hexagon relations. And the big difference between a Hopf algebra and a Hopf monoid in this arbitrary braided monoidal category is substantially given by the compatibility between the coproduct and the product. So the fact that delta is multiplicative. In fact, as you can see here, for this condition, we apply delta on A and delta the flip, and then multiplication tensor multiplication. But if we are considering an arbitrary n, we have to use the braiding of the category M instead of the flip map, which is in fact the braiding of vector spaces. So now we can introduce the notion of Drinfeld post-Hopf algebra. A Drinfeld post-Hopf algebra is just the datum of an algebra, which is also a co-algebra, equipped with a morphism S from H to H, which is a convolution inverse of the identity, and a morphism of coalgebra, these are Kun from H tensor H to H, that satisfies 1 and 2. So the first one just tells you that the product is linear with respect to this morphism. And the second one, this is the form associativity, as you can see. Moreover, we also ask that this map, when it is regarded as a morphism from H to the endomorphism of H, so that to any X associate the endomorphism, that it is exactly acting with X from the left, is convolution invertible. And this means that there exists a unique morphism beta, again from H into endomorphism, such that this compatibility condition is satisfied. In fact, you can see that we are using the coproduct on H for x1, x2. Then we apply alpha and beta, or beta and alpha. And then we use the product of the endomorphism, which is given by the composition. And this has to be the unit here, which is in fact do the epsilon, the co-unit of H, and then just you have the identity as an endomorphism. So alpha is convolution invertible, means exactly this. And we also require that the co-unit is a morphism of algebras, while delta is unitary, but it is not multiplicative in the usual sense. In fact, it satisfies this condition here, which is different from this, in fact, as you can see. And now we also require that once we define a new operation bullet in this way, and the new morphism S harpoon in this way here, using beta and S, and a right, let's say, harpoon using, in fact, this S and this bullet, in this way, this S has to be anti-commutative, and the pair left harpoon and right harpoon has to satisfy this condition here. And now we will explain in a minute why all these conditions. First, just tell that a morphism of Drinfeld post-Hopf algebras is just a morphism of algebras and of coalgebras G, which is compatible with the harpoon. And we denote this category in this way, Drinfeld post. Now, an observe cocommutativity. Here you can see that we can change x4 with x3, and then using alpha and beta are convolution invertible, and so this vanishes. And in fact, we obtain exactly that delta of xy is x1, y1, x2, y2. Moreover, one can prove that also the S is not just anti-commutative, but it is also commutative, and trivially, this condition is clearly satisfied. In fact, you can interchange x1 with x2 and y1 with y2. So in this case, if we assume cocommutativity, we recover the notion of cocommutative post-Hopf algebra given by Sheng and Tang. So if you assume cocommutativity, cocommutative Drinfeld post-Hopf and cocommutative post-Hopf are the same category, while if we remove cocommutativity, this is not the case. In fact, our delta is not a morphism of algebras, and our starting H is not a standard of algebra. We have this result when we start with the Drinfeld post-Hopf algebra and we define bullet and S as before. Then we have the so-called subjacent of algebra. This definition is given in analogy with that given by Li, Sheng, and Tang. And so, considering the bullet and S defined before, with the same unit of product and epsilon, we have a standard called the subjacent of algebra. Moreover, if we consider primitive elements of H, which are just given by the element of H, such that the coproduct over X over the element X is X tensor 1 plus 1 tensor X, this is a post-Lie algebra, considered in fact with the bracket given by just the commutator and with this morphism here. So when we start with the Drinfeld post-Hopf algebra, we obtain a post-Lie algebra considering primitive elements. So we obtain in fact this when we start with a Drinfeld post-Hopf. If we consider this morphism here, this harpoon here, and the adjoint coaction, so a coaction is just dual of an action, so it satisfies co-associativity and co-unitarity again. And in this case, we are choosing the so-called adjoint coaction given by this expression here. So with this action and this coaction, our H becomes a Drinfeld modulus. Drinfeld modulus over the subjacent of algebra. So in fact, the Drinfeld modulus, a left Drinfeld modulus is just a left module, which is also a left comodule with a compatibility between these two structures. So with the starting action, this left harpoon and the adjoint coaction, this is a Drinfeld module on the subject of algebra. And moreover, it is in fact a Hopf in this category. So H dot the unit 1, delta epsilon, and S are not a standard Hopf algebra, but a Hopf algebra in this category here. So in fact, as we said here, what changed is this compatibility condition. And in fact, in our case, we are using the braiding of Drinfeld modules. And we have exactly this relation here. So the braiding in our case is this. So to an A tensor B, it associates alpha of A1, which is an endomorphism, applied on beta of A3 over B tensor A2. And you can see that if we assume cocommutativity, we can interchange A3 and A2, and then using the fact that alpha and beta are convolution invertible, and we obtain the flip map. And so under cocommutativity, the braiding becomes the flip map, and so this Hopf algebra becomes a standard algebra in the category of standard of algebra in vector spaces. And so we recover, in fact, cocommutative post-Hopf algebra. Now we can consider the setting of Rota-Baxter operator, and we introduce this definition. So in the paper, we also introduced different notions of pre-Rota-Baxter operator. Now I just introduced the specific notion that we need in the following to build the adjunction. So start with an Hopf algebra H and K, which is an Hopf algebra in the category of Drinfeld module with an arbitrary action of H over K and a coaction given by this. So we are substantially just using the adjoint coaction of H just through a morphism R, which is a morphism of coalgebra. So we can say this in this way. So H is an Hopf algebra, R is a morphism of coalgebra, and K is also a Hopf algebra in the category of Drinfeld module with an action and this coaction here. So this R is called a Drinfeld relative Rota-Baxter operator if these two conditions are satisfied. So the first one is exactly the one that is also assumed by Sheng and Tang in their definition of a relative Rota-Baxter operator. And so, in fact, mimic the one of post-Lie algebra and tells you that the product of two images is just given by RA and RV, is just given by the image through R of this product here, where in fact we use the action of H over K. And we also have another additional condition involving the antipode that is not present, in fact, in the case of relative Rota-Baxter operators. A morphism of Drinfeld relative Rota-Baxter operators from an R to an R prime is just given by a pair of morphism of algebras and coalgebra, F and G. So F goes from to the domain of R to the codomain of R to the codomain of R prime, while G goes from the domain of R to the domain of R prime, such that, in fact, these two equality are satisfied. So F composed with R is R prime composed with G, and G over the action is the action of F over G, essentially. And we denote this category in this way here. And now, if we assume, in fact, cocommutativity also in this case, we can see that this coaction becomes trivial. And so the braiding of Drinfeld module just becomes the flip map, and so K becomes a standard Hopf algebra, a cocommutative Hopf algebra. And so, in fact, we recover the definition of a relative Rota-Baxter operator, which is a morphism R between cocommutative Hopf algebras satisfying this first condition. In fact, the second one is automatically satisfied if it is cocommutative. In fact, we recover the definition of relative Rota-Baxter operator on a cocommutative Hopf algebra given by Lie, Sheng, and Tang. And as proved by them, also in our case, the following result still holds true. If we start with the Drinfeld relative Rota-Baxter operator, if we restrict it to group-like elements of the Hopf algebra K, which are the elements such that the delta of K is K tensor K, and this forms a group. If we restrict it to group-like elements, this goes from group-like elements of K to group-like elements of H, and it is a relative Rota-Baxter operator between groups. While if we restrict it to primitive elements of K, so it goes from primitive elements of K to primitive elements of H, this is a Rota-Baxter operator between Lie algebras. Okay, and we have this result here. We have an adjunction, in fact, between these two categories, the one of Drinfeld post-Hopf algebra and Drinfeld relative Rota-Baxter operators, where the functor L and R are defined in this way. When you start with Drinfeld post-Hopf, as in the Lie algebra setting, let's say, you can consider the identity from H to the subjacent of algebra as a Drinfeld relative Rota-Baxter operator. In fact, I recall you that the subjacent of algebra is standard of algebra, while the starting structure is an of algebra in the category of Drinfeld module over the subjacent of algebra. And okay, to a morphism of Drinfeld post-Hopf algebras, G, it associates the pair GG as a morphism between the respective Rota-Baxter operators. On the other hand, the functor R associates to any Rota-Baxter operator R from K to H, as in the Lie algebra setting, the Drinfeld post-Hopf algebra K with an action of K over itself, in fact, obtained by using the action that we have of H on K. So we just, an action of A over B is just do the image of A through R and then use the action that you have of H over K. And to a morphism of Rota-Baxter operator, which is given by a pair of morphism F and G, you just consider G, which becomes automatically a morphism of Drinfeld post-Hopf algebras. So we have an adjunction, and in fact, if we assume cocommutativity, as we said before, K becomes a standard of algebra, and then we recover the result, the adjunction between cocommutative post-Hopf algebras and relative Rota-Baxter operator on cocommutative of algebras given by Lie, Sheng, and Tang. Once one consider bijective relative Rota-Baxter operator, we obtain an equivalence with the category of Drinfeld post-Hopf algebra. Okay, in the following, we want to define a different category, which is isomorphic to this of Drinfeld post-Hopf, and go into the direction of solution of the quantum Baxter equation. So, first of all, in a paper with Ferri, we introduce the notion of Drinfeld brace, which is the datum of algebra H bullet, a second operation dot on H, and a second linear map S from H to H, such that, in fact, H with this dot, the same unit, one, the same coproduct and the same co-unit, delta and epsilon, and this S is an of algebra in the category of Drinfeld module over H bullet, with action defined in this way here, and coaction given again by the adjoint coaction. If we define a right harpoon similarly as before in this way, again, this pair here has to satisfy this condition here. And finally, the two operations, bullet and dot, satisfy the famous brace compatibility condition, which is a compatibility between bullet and dot, involving the antipode of this of algebra here. And a morphism of Drinfeld brace is just a morphism of coalgebras. The coalgebra structure of a Drinfeld brace is unique, is one, while you have two algebra structure. In fact, you require also that F is a morphism of algebras with respect to both the operations. And I again want to observe that if we assume that H is cocommutative, again, the adjoint coaction becomes trivial, and so the braiding of Drinfeld modules becomes just the flip map, and so we recover the notion of cocommutative of brace given by Angiono, Galindo, and Vendramin. So an of brace which is cocommutative, so such that is delta satisfy delta is equal to delta followed by the flip map. So we can define an ISO now between the category of Drinfeld post-Hopf algebras and Drinfeld brace. So when you start with the Drinfeld post-Hopf algebras, which is a datum of this form, where in fact H is an algebra and it is also a coalgebra with an antipode and an action that satisfies the condition of before, we know that we can define the so-called subjacent of algebra, which is an of algebra structure given by this bullet and this S here. And this datum is the datum of a Drinfeld brace. In fact, as you can see in the definition, you need that the first structure, so the dot one, is an of algebra in the category of Drinfeld modules over H bullet. And this is what happens in the case of post-Hopf algebra. H dot is an of algebra in the category of Drinfeld modules over the subjacent of algebra. On the other hand, if we start with the Drinfeld brace, we just keep the first structure and we define the action in this way here, which has convolution inverse given by this, so using the antipode T. So these two functors give an ISO of categories, and if you assume cocommutativity, this ISO in fact restricts to an ISO between cocommutative post-Hopf and cocommutative of braces. Now we can define another action, another category, the one of match pair of action. So we start with an Hopf algebra, H, and a match pair of action is just given by a pair of a left and right H action on H, so action of H over itself, such that H becomes a left and right module coalgebra with these two actions. And these three conditions are satisfied. So the first two just tells you how an element acts on a product. And again, the second tells you how the right action acts on a product, while the third one tells you that the product of two elements is just given by this product here, where you use the left and right action. And a morphism of match pair of action is, again, just a morphism of algebras, such that it is compatible with the two actions. Now, just some observation. If we assume 1 and 2, these two conditions here, but instead of 3, we consider this condition here, that is the one that we see before twice, we have the notion of the match pair of algebras in the sense of Majid. And these conditions, so 1 and this here, are exactly those that you need to define the so-called double cross product of algebra on H, which is just given by H tensor H as a vector space, with this product that deform the standard tensor algebra product using the left and the right action, unit just given by 1 tensor 1, and the tensor product coalgebra structure. You also have an antipode obtained using left and right action, but now we don't need it. An observation, if we assume, in fact, this condition here, instead of this other one, this implies this condition. And so every match pair of action is, in fact, a match pair in the sense of Majid. And more precisely, match pair of action are exactly the match pair of algebras, such that the multiplication of H, seen as a morphism from the double cross product to H, is a morphism of algebras. And now we have, in fact, another ISO of categories between match pair and Drinfeld braces. And so this tells us that Drinfeld brace and match pair of actions and Drinfeld post-Hopf algebras are isomorphic as categories. And this ISO is given by these two functors. So if we start with a match pair of action on of algebra H bullet, we can define a new product dot using bullet T, the antipode of starting of algebra, and the left action, and a new antipode S obtained using by, again, the left action and T, and these give us a Drinfeld brace. On the other hand, if we start with the Drinfeld brace, we just keep the second structure, which is in fact a standard of algebra, together with this action defined in this way. So the left is defined in this way, and the right action is defined using T. And these give us, in fact, a match pair of action. Recently, it was proved in a recent paper by Lee that match pair of action, in fact, produce solution of the quantum Yang-Baxter equation given by this. So to an X tensor Y, you associate this. So X1 acting from the left over Y1 and Y2 acting from the right over X2. This is a solution of the quantum Yang-Baxter equation, and R is involutive if and only if the multiplication dot is braided commutative. In fact, we know that when we have a Drinfeld brace, the dot structure is the Hopf algebra, let's say H dot, is an Hopf algebra in the category of Drinfeld module. And so R is involutive if and only if the product is multiplicative in this category. So in fact, braided commutative. So this relation holds. Now, and this also answers a question that we left open in our paper. And now I want to just see some special Drinfeld braces coming from co-quasi-triangular of algebra. So I want to recall first the definition of a co-quasi-triangular of algebra. So Hopf algebra H is co-quasi-triangular if it is equipped with a convolution invertible morphism R from H tensor H to the base field, satisfying these three axioms here. If the convolution inverse of R is given by the opposite of R, so R composed with a flip map, then H is called co-triangular. It is well known that co-quasi-triangular structure corresponds to R in bijective correspondence with braiding on the category of right comodules. In fact, this axiom here, so the first one, just tells you that the braiding is a morphism of comodules, while 2 and 3 just corresponds to the hexagonal axiom. And co-triangular structure, so those are such that the convolution inverse is given by the opposite of R, corresponds to symmetric braidings. So braidings such that are involutive. And in fact, the braidings are given by this. So to any X and Y comodules, the braiding is given by a flip map on the, let's say, we first do coaction on X and Y. And X1, which is something in H, and the coaction over Y. So we obtain Y0, which is in Y, and Y1, which is in H. And then on the part in H, we apply the R. But now, when we have quasi-triangular structure, we can consider also a different braiding operator given by this expression here. And you can see that we use R-1, then flip in the middle, and then R. And this is a braiding operator that also extends to a braiding for bicomodules. And from this, you can obtain a left and right action just by considering identity tensor epsilon over the braiding operator and epsilon tensor identity over the braiding operator. You obtain a left action and a right action of H over itself. And this pair of action, in fact, form a match pair of actions in the previous sense. So since we have a match pair of action, we are able to build a Drinfeld brace using this action here. So we have this theorem here when we start with the co-quasi-triangular of algebra, then we find dot and the new answer. I recall you that dot is defined in this way here, and S is defined in this way here. In this case, we are just using the action coming from the co-quasi-triangular structure, so exactly this one. And so we obtain a Drinfeld brace where dot and S are defined in this way here. But now one can recognize that the new Hopf algebra, H dot, which is in fact an Hopf algebra in the category of Drinfeld modules, coincide exactly with the transmutation of the Hopf algebra H bullet in the sense of Majid. So in fact, this match-pair function is in a sense generalized transmutation in the sense of Majid. Okay, and now I would like to finish by consider some specific examples, so some concrete example, just to show you how this works. And so for three specific examples, I want to give you the Drinfeld brace structure and the Drinfeld post-Hopf algebra structure. So let's start with the first one, so the Swidler Hopf algebra. Assume that the base field has characteristic different from 2. Then we know that the Swidler Hopf algebra is the algebra generated by two elements, G and X, subject to this relation. I just put bullet because this will become the second structure in the Drinfeld brace datum. And so in fact, the product that corresponds to the bullet in the previous definition. So the relation just tells you that G square is 1, X square is 0, and X and G anti-commute. The Swidler Hopf algebra is a Hopf algebra with a group-like structure for G, so delta of G is G tensor G, while X is skew primitive, so delta of X is X tensor 1 plus G tensor X, and the antipode, that again we denote with T because it will become the second antipode in the Drinfeld brace datum, fix G, while on X is given by XG. It is known that there is an exhaustive one-parameter family of co-quasi-triangular structure, which are all co-triangular in this case. Given by this, you can see that when you don't consider X, so on 1, 1, 1G, G1, and GG, you have 1 or minus 1. While if you have X on just one of the two entries, you have 0. While if you have X on both entries, you have K, or just minus K. Now, using this, we have, in fact, we can define a new product using in this way here, and the new antipode. And precisely, the new product give us an algebra generated again by G and X, but with this relation, so G square is 1, X square is not 0, but it is, in fact, the scalar meter, the parameter K, which multiplies 1 minus G, and in this case, X and G commute. And one can also define S in this way. In fact, S over G is G, while S over X is minus XG. And with this dot and S, we obtain an Hopf algebra in the category of Drinfeld modules over the starting Swidler Hopf algebra, standard Swidler Hopf algebra, and these two structures together forms a Drinfeld brace. Now we can also define, in fact, the left action in this way here. So if we keep the dot structure with this new action here, we obtain a Drinfeld post-Hopf algebra, where the action is defined in this way. G is the action of G over 1 and G is the identity, while it is trivial, and over X and XG is just given by minus X and minus XG, while X gives 0 when X over 1 and G, while gives these guys here when acting on X and XG. And for XG, you just have these with different signs. And to form a Drinfeld post-Hopf algebra, I also must tell you how the convolution inverse of this map is built, and it is exactly this one, this beta, which is as the harpoon, just for these two guys. In fact, you have to change signs. For the other is identical, you're saying. So we can generalize also this example. So instead of considering the Swidler Hopf algebra, we can consider the Hopf algebra En. So again, we start with a base field which has characteristic different from 2. And we consider the Hopf algebra generated by an element G and n x, so x1 to the till to xn, with this relation here. So as before, g square is 1, and xi square is 0 for all I. Xi and g anti-commute, and the same xi and xj for different I and j. That the G is group-like. Xi again is Q primitive, and the antipode T fixed G, while over Xi is given by Xig. So one can see that if we consider E1, so just with one X, we recover exactly the Swidler of algebra. Also for this, we have a quasi-triangular structure given by this. So this part is exactly the same of Swidler. So 1, 1, 1, and minus 1. Also, when you have just an X on the left or right tensor, and you have 0, as before. But now we don't have just an X, but we have n X. And in fact, we don't have just a scalar meter, one parameter, but we have a matrix Aij, which depends on the X. So R over Xi and Xj is given by Aij. And so for the other guy here. And so in fact, you can see that if we just have one X, we recover exactly the quasi-triangular structure of the Swidler of algebra. Now we can define, in fact, a new algebra structure generated by G and this Nx, where the relation change. In fact, we have that G square is 1. Xi and G commute, in this case, for all I. And if we consider Xi with Xi, you can see that we recover exactly this relation here, Swidler, just because the base field has characteristic different from 2, while for I and j, we have that xi dot xj is minus xj dot xi plus this guy here. And this new product with a new antipode S defined such that it fixes G, and on an xi, it is given by minus xig, in fact, give us an Hopf algebra in the category of Drinfeld module over the Hopf algebras En. And again, we obtain a Drinfeld brace, putting together these two structures. If now we keep the dot structure, so En dot 1 delta epsilon and S, we can define an action in this way. So it is the same that we have for Swidler, but in fact, again, instead of having K here, we have an Aij, which depends on I and J since we have different X. And this forms a Drinfeld post-Hopf algebra where the convolution inverse beta of alpha is given explicitly by this other table, where in fact we just change the sign of this with respect to the previous table. And now we finish with last example, which is given by the Hopf algebras SLQ2. So start with the complex number different from 0 and consider the algebra generated by 4 elements, A, B, C, and D, modulo this relation. We can see that we have some deformed commutativity condition. So B, A is QAB, and so on. D, C is QCD. CA is QAC. The only two guys that commute are B and C, while for A and D we have this more different relation. And we also impose the so-called quantum determinant condition. It is known that these form a Hopf algebra with the so-called comatrix commultiplication. So the delta of an element A has to be read as A tensor A plus B tensor C. So just as a product of matrices. And so on, the delta of B is A tensor B plus B tensor D. The co-unit is 1 over A and D, while it is 0 on B and C. And the antipode T just interchange D and A, while it fixed C and B with some scalar. it is known that this is co-quasi-triangular with this structure R. And now we can define, in fact, a new product. We have a new algebra generated by A, B, C, D with this new relation here. So again, we have that these guys, we have some deformed commutativity condition. Instead of having Q, we have Q to minus 2 or Q squared. And you can see that in this case, A and D commute. While for B, D, and BC, we have more strange relation respect to the one that we have before. And now we can also define a new antipode S, which, again, S of D is A as before, while also S of C and S of B are fixed in a sense that you just have a scalar, which differs from that we have before, while S of A is not given by D as before, but it is Q to minus 2D plus something in A. And these, in fact, give us an Hopf algebra in the category of Drinfeld modules over the Hopf algebras SLQ2. And these two structures, again, give us a Drinfeld base. And now just considering the first Hopf algebra structure, so the dot one, we obtain a Drinfeld post-Hopf algebra once we define an action in this way here. So you can see that A acts substantially as the identity. In fact, you just have A, B, C, D. For B and D and C, you just have some scalar, Q minus 1 and Q, and the same D over the elements, while C acts on everything just as 0, gives 0 on every element, while B gives 0 when acts over B, while on these other elements give this. And this action here has, in fact, a convolution inverse that tells you that, in fact, H dot is a Drinfeld post-Hopf algebra, which is given by this table here, which is the same as before. You have just to change on the first and last line Q with Q minus 1. Again, here we have all 0, and this line is obtained from this one just by multiplying with minus Q. And so these give us, in fact, a structure of Drinfeld post-Hopf on SLQ2. With this, I finish, and I thank you for attention. Just put some references.
So thank you, Andrea. Are there any questions or comments? Don't see any, so I can ask a question. In the classical case, cocommutative post-Hopf algebra, classical Hopf algebras, I think that you can deform the product to obtain a new Hopf algebra.
Okay. In the cocommutative post-Hopf, you will say.
Yes, the cocommutative. You need the cocommutativity at a point in the same way as for postly. You know, you have a first bracket, you can deform it with the help of the action. Do you have something similar in your setting?
I didn't know. I never thought about this, but it's interesting. So you say that when you have cocommutative post-Hopf, but when we have cocommutative in our category coincide with the one of post-Hopf. So cocommutative Drinfeld, I can show you. Drinfeld, yeah, exactly. Drinfeld post-Hopf is given by this category here. And when we assume cocommutativity, this becomes a standard morphism of algebras. And also this other condition here that this S is anti-commultiplicative is automatically satisfied. In fact, it is also commultiplicative. And also this condition here is trivial, as you can see, if you can change x1 with x2. And so cocommutative Drinfeld post-Hopf are cocommutative post-Hopf. So,
yes, you say so.
You can do the same stuff if you assume cocommutativity. You have also this result here is substantially the same also for primitive elements, because in fact under cocommutativity they are the same category. So the same result all in this case, in the sense that you what really differs is when you remove cocommutativity. I don't know if you remove cocommutativity. I don't know if you are able to define.
What I know, that in the classical case, as I said, you can deform the product of another product on your Hopf algebra, and it's still a new Hopf algebra, but you need the cocommutativity. Without the cocommutativity, it doesn't work. You can obtain a new product, but it's not associative. So
I see.
It's a little bit useless.
Maybe in this case, since if you remove a cocommutativity, we have different definition. Maybe it becomes an Hopf algebra. I don't know. I have to see the definition of this deformed product because I don't know. Yeah, if we are able to define something similar for Drinfeld post-Hopf, let's say. Again, without assuming cocommutativity otherwise.
Well, maybe you already have it because you work in Drinfeld setting, so you already have two products.
Yeah.
The big dot and the small dot, if I remember correctly.
Yeah.
So maybe that's the point with cocommutativity.
Maybe. Thank you for the comment.
I had another question. In the classic, for post-Hopf algebra, if the first structure is trivial, if the bracket is trivial, you obtain pre algebra.
Yeah.
Do you have something like this, a sort of a pre-setting instead of the post, where
the pre-setting
would be trivial or something like this?
Is in the case of as in the case of post-Hopf. So in the case of post-Hopf, pre-Hopf algebra are when the multiplication is commutative. In our setting is when the multiplication is braided commutative, because we are in the category of Drinfeld model.
Okay, I understand. This is just the braided commutative case for pre.
Exactly.
Okay. Probably it's easier to work with it.
Yeah, it's more natural when in some sense is natural when you remove to commutativity to goes in something which is not a standard Hopf, but an Hopf algebra in a different category, which collapse on vector spaces just under the assumption of cocommutativity. Yeah.
Okay, I think that's natural. And you gave some example of quantum group SLQ, SL2, SL2Q, so something like this at the end. Do you look at other quantum groups?
No, I didn't look at it. Yeah. I didn't look at it.
So thank you very much for your answer. Are there other questions?
Thank you again.
I don't see any question. There is an invitation on the chat from Florin Nichita. So, Andrea, thank you again for your talk.
Thank you.
So thank you again.
Can you share?
And thank you everybody for your participation. And see you later.
Thank you. Bye.
Bye.
Bye.